Welcome, everybody. This is the August 1st, 2023 occurrence of the P4.org Open Source Developer Days meeting. Welcome. Today we have a speaker, Robin Das. He will pronounce his name correctly for you, I hope. And I'd say take it away, Robin, and please introduce yourself.
Okay, hello everyone. So my name is Debobroto Das Robin. So back to in my country, usually people call it the last name. So just go with the Robin. That's totally fine for me. So I am currently a PhD student at Kent State University. Uh, I am at the final phase of my PhD. You can say it's just all but dissertation. And I have recently joined with Cornelis Networks in my CPT for curricular practical training. So I'm working with them at this moment. But this work I'm going to present here, the open source compiler backend for V1Model switch, it is actually totally done in my PhD work. So as I have mentioned, I am a PhD student at Kent State University, and my PhD supervisor is Dr. Javed Khan. So if you have any question at any moment, just let me know. At any time, you can ask question, no problem. So first of all, the outline of the presentation. So I know every one of these group are super specialist about the P4 and related hardware, but I have added some background so that if some new people watches this video or presentation, they can get idea. So then after the background, I will talk about what's the motivation behind working on this project. Then I will talk on the structure of the compiler backend as I have implemented, and I will show you some performance at the end of the presentation. I will give you a really short demo, just running a Python program. So, and after that, if you have more questions, I'm open for that. So a bit of background. So first of all, what is at the starting, we need to look at the RMT switches architecture. So RMT switches contain one or multiple pipeline. So every pipeline is basically contains of some of the components. Out of them, 3 are the major reconfigurable components. So first one is the packet parser. Second one is the packet header vector. So the packet header vector is the container that holds the header fields and carries through the rest of the pipeline. And this packet header vector or parser or any other reconfigurable components, they have limited amount of capacity. The third major component of this pipeline is the match action stage. So here you can do some kind of match on some packet header field, and based on that matching result, you can do some or execute some action. So these are the 3 major reconfigurable component, and a very basic level of P4 program here. So I have taken the P4 program from the GitHub repo mentioned here. So P4 is basically a bit of high level program, not like Python, just a bit more high level than the machine level programming. So you can write packet parsing and processing logics, but the language constructs in P4 is not fully aligned with the hardware capabilities. So as I have mentioned in previous slide, that there are 3 major reconfigurable component. So to program them in P4, we can say that there are 3 major parts. First one is the header definition. So based on those header definition, you need to write a packet parser. So you write the parsing logic here, and then you have the control flow. So that control flow basically guides what match and action will happen in the match action stages. So how do we run these P4 programs into a RMT hardware? So of course, for that, we need a compiler. So this is a very bare bone example. For example, we have a packet parser here. So we have to map this parsing logic into the programmable parser. Then the programmable parser will store these fields in the packet header vector. packet header vector is a container that can hold several header fields. Then it will carry the header fields through the rest of the match action stages. Now, in these match action stages, you have to implement these packet processing logic. Say, for example, here in this example, we have a very simple packet processing program that looks whether if we have a IPv4 table, if it is matched successfully, then it will not execute this part. Otherwise, it will go to the IPv6 matching. So if we want to map that program into a RMT hardware, this is just an example. So say for the IPv4, we can accommodate the IPv4 table on this match action stage. And for the IPv6 part, we need rest of the match action stages. So a compiler needs to compile these packet programs and map into those hardware constructs, native hardware constructs. So that's the task of a P4 compiler. Now, what's the challenge in compiling the P4 programs? The main challenge here is that the native hardware constructs, they have limited capabilities. But when you are writing a P4 program, from a data plane program developer's perspective, you are not really thinking about what is the capability of the real hardware, what is the table length a match action stage can afford. So you are not aware of these things, or you are not thinking about those things all the time or in a very realistic hardware sense. So if we want to run our P4 program on this kind of hardwares, we have to be sure that our program can be accommodated into these hardware stages. Say, for example, in our case, for this simple program, say for the IPv4 table, we can map it to the first match action stage. But for the IPv6 table, we need a large enough table, which we cannot accommodate in the n number of stages available in the hardware. On that case, we cannot run the P4 program on this hardware. So this is the main limitation. So in this example, I am just giving the high level description of the match action stages, but we can go for the similar constraints applicable for parsers, also the packet header vector. Even for the match action stages, we can go for finer granularity. For example, every match action stages have a limited number of ALU or maybe some number of extern units. So you also need to make sure that your P4 program is accommodatable within that hardware limit. So the compiler's challenge is that you have to find a conformant mapping of your P4 program onto this hardware. So in algorithmic sense, these problems are computationally intractable. So if you're interested, you can look into the paper. I have just mentioned one paper. There are a couple of other papers, I think. So if we look into the P4 language ecosystem, so from a P4 developer's perspective, they start developing a P4 program. So this P4 program is based on some specific hardware architecture. Say, for example, someone is writing a P4 program for V1Model or maybe Tofino 1 or Tofino 2. So these two things are provided to the compiler frontend. And compiler frontend and midend, they do the program syntax and some semantic analysis. They do some kind of optimization. So this part is available as P4 compiler, P4C. So from the P4 consortium. Now, they can generate an intermediate representation of the P4 program. Now, if we want to run this program, so basically this P4 program is converted into the intermediate representation. So we need to pass that to a compiler backend so that it can it can compute the mappings. So if we want to map a P4 program, we need to specify what are the resources and what are the amounts, how many match action stages, what are the number of table entries you can put in every match action stages. So these kind of informations are needed for the compiler backend. So we need another information here. So the hardware resource description. So typically this part is closed source. Like for the, I think Tofino, you have the P4 Studio, and couple of I saw AMD also has a P4 architecture, P4 hardware. I forgot their compiler name. I don't know it actually. So this compiler backend, they find the mappings, then these mappings are converted into the corresponding machine instructions, and they're loaded into these native hardware units. Then the programmable switch can process a packet. Now in this ecosystem, you can see the P4C is open source, but the compiler backend is closed source. Now, what's the implication of this closed source compiler backend for the research community? So out of these implications, that is the actual motivation of my doing this work. So first of all, if we look into the research papers, most of the papers, only a couple of people have real life RMT ASICs and their compilers, but majority of the people are in the research community, they mostly use the P4C compiler backend. Sorry, I should have written this front end, my bad. And they run that compile program on the BMV2 backend. So the limitation of this P4C and BMV2 composition is the main driving goal behind my research. So what are the limitations of this P4C and BMV2 backend? First of all, you are writing a P4 program, and if you run that BMV on the BMV2 backend, you are not really making sure that whether your program matches the actual hardware limitation of a real hardware. If you run any arbitrary P4 program, the BMV2 based backend will just run it. So it's not a realistic scenario. You don't even know whether your P4 program will be feasible to run on a real hardware. For example, here, say this IPv6 table, if it needs, say, like 34 stages, but if you have only, say, 32 stages, you cannot run that program on the switch. So we need to make sure, if we want to say that our P4 program is feasible backend, it's not possible. Second thing, say we have a program. Now we want to get real fine-grained analysis of the resource consumption. Say, for example, you are running a program that needs, say, 100 ALUs in one stage, or how many stages it actually needs. Say, for example, you are running a program for in-network computation. If you have only, say, 32 stages in your hardware and you are using 31 stages for that in-network computation, you will have very limited amount of stages for doing real packet forwarding tasks. So on that case, your program may be totally infeasible. So we want to know from a research perspective, what are the actual resource consumption of a P4 program? With BMV2 backend, that's not possible. Then say we have a in-network computation or any other feature we want to implement in a switch. Now, people propose different algorithms for implementing same features. Now say we have a P4 program 1 and another P4 program 2. They're implementing the same feature, but the program 1 needs P number of match action stages and program 2 needs Q stages. Now, of course, if P is less than Q, then the program 1 is much more efficient. So on that case, how we can compare efficiency of different P4 schemes? We also want to know that. That's not possible to know with a BMV2 backend. Then one of the major driving goal behind my work is that I wanted to implement new extern. So the V1Model mostly have some register extern and some hash-based extern. So I wanted to implement new extern units so that we can extend the capability of a switch, or we can experiment with new type of externs. So If you want to implement a new extern, there are a lot of high-level synthesis framework. You can use them. But if you want to make sure that your P4 program is capable of implementing that with the hardware, with all the resource limitations, we need compiler backend. Now, with the P4C compiler front end, you can add a new extern easily on the front end, but for the backend, there's no real option. So for BMV2, we need some kind of option so that we can experiment with new externs. Then the compiler backend, while mapping a P4 program into the real hardware natives, so it needs to handle a couple of computationally intractable problem. So if we want to find a optimal solution, of course, for a computationally intractable problem, it may take really long time. So when you are developing a P4 program, maybe you are, most of the cases I have faced, and I have talked with a lot of people in the research community, they are working on a small algorithmic feature. Maybe it will take 4 or 5 stages. So they want to get a quick decision on the feasibility of a P4 program. So on that case, we can use heuristic-based mapping algorithm. So this has 2 aspects. First of all, we need a quick decision making in development time, and also we want to develop new kind of mapping algorithms. So if the compiler backend is closed source, you don't have access to that part. So again, BMV2 doesn't consider the actual hardware limitation of a real hardware. So we also cannot do that. So we need some kind of framework to do that. So I just discussed this, so I am skipping this slide. So these are the 5 major limitations of closed source compiler backend. So I wanted to get rid of this thing. And I want to mention that for the whole of my PhD life, I didn't get any access to any real RMT hardware. So I was kind of desperate. So I wanted to build something so that I can check my other programs' feasibility. So I have built a load balancer, a quality of service or routing scheme, but I couldn't check them in real hardware. So that's why I jumped into this project. And I tried to build a compiler backend specifically for V1Model switch. Now, why I have selected the V1Model? The first reason is that V1Model is a barebone RMT architecture. So you can add new extern, new match units if you want, and experiment with that. So if you add new register extern or stateful ALU that can do Tofino-like processing, you can do that just by extending the V1Model. Then another reason is currently this is P416, the P416 version is going on, but there's a large number of research works, they have used the P4 version 14. So we can convert a P414 into 16, but the P414 basically use the V1Model. So if we use the V1Model as the compiler backend, so all the people can port their P414 program into 16 and use my compiler backend. So that's why I went with the V1Model. Now, in the whole P4 ecosystem space, so my compiler backend actually works here. So typically a P4 developer, we will provide their P4 program into P4C, and it will generate the JSON representation for the BMV2, the intermediate representation. So there's the input one of my compiler backend. Then if you want to check your P4 program's feasibility on a specific hardware, you need to specify the resources. So in P4C toolset, I think there's no such option. So I have built a simple JSON-based description language to describe the resource amount of a V1Model architecture. So these are the 2 inputs of my compiler backend. So using these 2 compiler backend, my compiler backend will generate these 3 types of mapping: the physical header vector mapping, the parser mapping, and the table dependency graph mapping. So a bit more about the input one. So that is the JSON representation for the BMV2. Now the P4C toolset can give you the JSON representation for the BMV2 backend is not the real intermediate representation, because the P4C gives even one previous stage intermediate representation. I have not used this because that is a bit hard to understand and tough to parse, but the BMV2 JSON is easier to parse, simple to understand, and of course that have a nice structure that will reduce my development time. And this, most importantly, that JSON is also actually a target independent representation. So the whole goal of intermediate representation is making target independent so that I can plug into my compiler backend. So that's why I picked this one. For the second input, we need to specify what are the hardware resource limits of every hardware components. To do that, I have actually modeled the whole RMT architecture and parameterized every component. So for example, here the parser unit, the programmable parser, then the packet header vector, it has different bit width containers, then the match action stages. So you can actually specify the resource amount of all those units into this hardware specification. This is a simple JSON specification. For example, here I have a PHP specification. So you can look at here the header vector specs. So it has 3 bit width containers: 8 bit width, 16 bit width, and 32 bit width. Now it has 100 piece of 8 bit width packet header vector fields and 124 of 16 bit width and 96 of 32 bit width, just like this. So you can specify all the hardware components and their limits and their amounts. For example, every stage has some limited amount of SRAM. So you can specify the memory port width, port count, how many memory block you have, what are the block bit width, and how many rows that have. So you can specify all of them. So these are the two inputs. First one is the intermediate representation of P4, and this second JSON-based specification models a real hardware's resource. You put these two into the compiler backend. Now, how this compiler backend?
Question?
Yeah, sure.
So I don't know how much you know about how hardware looks, but one of the main constraints is the routing network.
Right.
So the fact that you have, some PHV capacities and some TCAM capacities is not as important as what can get where.
Mm-hmm.
There's no full interconnection network. You can't read, for example, all the registers in one stage and perform arbitrary operations on them.
Right, right. I will come into this a bit later. Just hang on. I'm coming to that part. So let me partially answer your question here. So for example, I have taken the model from the actual RMT paper, from the Dr. Nick McQueen. So say, for example, in a match action stage, you want to pass the header field as key to the match units. So there is a crossbar there. In the hardware specification, you can actually specify the bit width of the crossbar. So you can look at here, there is action crossbar bit width. So that is just one part I'm saying, but the other limitation you have mentioned, like you cannot access the SRAMs twice in a one stage, I will talk in later part. So now for the compiler backend, let's look at the workflow. So this is the high level workflow of the compiler backend. So first of all, you get a P4 program. That these are the components of a P4 program: the header definition, the parsing logic, then the packet processing logic. The P4C will generate the intermediate representation. So in the JSON based intermediate representation, you have header field list, the parse graph, and the table dependency graph. So our compiler backend will take this intermediate representation and the hardware specification. Then it will compile and generate these three types of mapping. So the first type of mapping. So we want to generate a mapping from the header fields to the PHP fields. So say, for example, if you have a 4-bit version field, you can either put it in a 8-bit PHP field, or you can also put in a 16-bit. But of course, 16-bit is waste. So you want to go for the 8-bit PHP field. So you need to find this kind of mapping. So this mapping is actually, you can formulate this problem as a multiple knapsack problem. So that will be computationally intractable. So I have implemented a heuristic based algorithm here, but you are free to implement any exact or optimal algorithm there. So in my heuristic, I have used the largest header field in the P4 program and tried to match it on the largest header field of the largest field of the PHP. But of course, say you have a 125-bit field in your header field. On that case, you cannot map that into this hardware. On that case, you can actually merge multiple packet header vector field. That feature is also there. So this is the basic implementation. There are a couple of limitations. First of all, my compiler backend, it doesn't support the header stack and union. And also, if you have a P4 program, I have calculated the P4 header field to PHP field mapping at the very initial stage. But actually, you can reuse the PHP fields. Say you have a PHP field and a header field used for only 2 stages at the start, but it is not used in rest of the stages. So you can reuse that, but I have not implemented that logic here. So anyone can write a new algorithm for that. Then if I move to the next thing, the parse graph to the parser TChem mapping. So the parser state machine here is based on the TChem based state machine. So again, I have taken that model from here, from this paper, from the same RMT group. So in the BMP JSON representation of the intermediate representation, they give you a parse graph for the parsing logic. So from that parsing logic, you have to map that on the actual parser hardware units. So this is the specification for a parser hardware unit, parser. Then it will actually calculate the TChem entries for that parser unit. So again, I have not used or implemented any new algorithm in this backend. I have just used their implementation and repurposed it. So that it can find the TChem mapping. And in their paper, they have used a graph clustering based heuristic. So anyone can also implement new heuristic algorithm for that part. So again, if you have written a header stack or union in the parsing, that will be not supported here. And in P4 language, you can actually parse a field and write some initialization stuff in the parser logic. That part is yet not supported in my compiler backend. Then for the actual control flow mapping. So if you want to map a P4 program into the hardware, so the P4 program's control flow can be represented as a control flow graph of where every nodes are actually some logical match action table. So we have to map that logical match action table into these physical match action stages. So again, this is a DFS based algorithm. So you analyze the dependencies. Of course, if you don't have dependencies, you can parallelize them and map two tables on same stage. But if you have dependencies, you cannot map them. So I have done that kind of analysis and mapped them onto the match action stages. So for example, here, this first table, the header control packet dot is valid. So that will be mapped here. Then you have IPv4 and some match control. So that will be mapped on same hardware, same match action stage. Then you have the IPv6 table. It will be matched on the next stage. It has couple of limitations. I should not say couple of limitations because you can do a lot of optimizations. So all the things are basically limitations. So I have listed some of the major among them. First of all, I have not done very good level of memory packing optimizations. Say, for example, you have two tables, say with 5-bit TCAM, 5-bit field match, and another has 10-bit match. So you can actually merge them, try to merge them into a same table and map them on same physical TCAM. I have not done this kind of optimization. Second thing is, the earlier question, the partial answer is here. Say for example, if you are running at 1 gigahertz clock speed, so of course you cannot access a SRAM twice. You can do read write, but you cannot do twice read or twice write. So I have checked that thing, and my compiler backend checks if your program has such kind of path in the control flow that it has to access the same SRAM twice in same clock cycle, it will reject the program. But say I have not experimented or tried to implement the logic for other clock speeds. Say, for example, if someone says that I have a 500 megahertz pipeline and you can do 2 read on the same SRAM, I have not checked this kind of thing. I have just, you can say it's kind of a fixed for that 1 gigahertz thing. Then I have done for the if-else conditions, I have done a flattening. So for the if-else, I have assumed that we have a conditional write ALU, so that if some condition is true, it will write a 1 bit on the field, and that field will be matched on the next stage. So I have kept like a fixed header field for carrying the branching conditions to the next stage. So you can actually configure the width of that, but at this moment, this is like 32-bit. So at every stage, you can actually carry 32 result of 32 if-else, and based on that, you can do some branching on next stages. But this is configurable, so you can increase it. Another thing is, for a P4 tables action, you can actually bind a direct counter to the table. I have not implemented that support. And also, a couple of people may find that atomic keyword is really important for them. So I have not implemented any kind of extra logic support for checking atomic keyword. So that's not there. So these are the major limitations here. So does that answer your last question?
Well, partially.
Yeah. So we can talk more on this question, like if you want.
How many more slides do you have for your talk? Maybe we could.
Yeah, I have a couple of more slides. Yeah.
Maybe save it for after the slide.
Okay.
Perhaps?
Yeah. Okay. Sure. Sure. Okay. So next question is how to extend the compiler backend. So you can actually write new mapping algorithms. So we have these 3 mapping parts. Parts are the PHP mapping and the TDG mapping. So there are actually 3 interfaces for writing these 3 mapping algorithms. So you can just replace any of the mapping algorithms and write your own mapping algorithm. Also, in the hardware specification part, I have kept the option for adding new extern, and so that you can add new extern or instruction set in the switch architecture. So you need, of course, if you add new extern, it will have some more limitations. So you need to write logic for that. One thing I want to mention that in the actual RMT paper, the authors have mentioned that all the ALUs can be activated or selected from a mux using all the header fields of the PHP. So for the externs, at this moment, this logic is same. But I think in real life, for every externs, you have to have a subset of the PHP field. So you have to write your own logic accordingly. I will update into the GitHub repo also. Then you can actually, if you have the V1Model support, I think we can go for the PSA architecture also. So I have actually started working on these two things, supporting new external instruction set and the PSA architecture. But these are kind of halted because of this is the final phase of my PhD, and I also joined with the Cornelis network. So having a bit of hard time in managing time. So these two features are actually in kind of partial implementation stage, or I will say very initial stage also. If you want to access the code, you can go to the GitHub repo. So here I have summarized a couple of important interfaces in the Python. I want to mention that the compiler backend is totally implemented in Python. So that's why all the interfaces are Python. So these are the 5 main interfaces you need to deal with if you want to extend the compiler backend. First of all, if you want to add some kind of new hardware specification or new kind of extern, so you have to change the hardware specification. On that case, you need to write a parser or extend the existing parser. So this is the this is the interface that will actually parse the hardware specification, and it will store it in this RMT V1Model hardware object. You can write any new object or interface for that part. Then the BMV2 JSON intermediate representation parsing, you have I have this interface, and that has a corresponding implementation. Couple of P4 keywords are not implemented yet, so I have listed couple of them in previous slide. So if someone is interested, they can extend the parser. Then for the rest 3 cases, 3 types of mapping. So these are the 3 types of interfaces. So you can just write new mapping algorithm there, and that will give you the result. So of course, all three are modular. So if someone wants to work on the first one, like header field to PHP mapping, you don't need to work on the other 2 things. You can keep them unchanged. You can just focus on any one of them. So that's kind of a modular architecture. I wanted to mention here that the new extern addition, for adding new extern into the instruction set. So I have a specific file where you can specify the extern instructions. So this is an example. As I have mentioned earlier, that for the extern units, I have not implemented the crossbar logic so that you can actually control which subset of the PHP fields will be activated for the extern units. So that part is not implemented yet. So I have a couple of future work plans here. So all the limitations I have discussed earlier, I am working on them and trying to solve them as quick as possible. Besides this, I am also trying to look into the PSA architecture, and I'll try to implement these 2 things maybe within this year. I have planned for that. And besides this, I have a couple of other goals, like after finishing computing the mapping, the visualization, there is no good visualization result. So I'll try to put some good UI or some good visualization for that. And also I have planned to integrate that with the Visual Studio Code. So these top 4 are my current higher priorities. And rest of the thing, I'm not sure about the final one, the multi-pipeline support, because I have mentioned earlier that I have a plan for experimenting with different clock speed, and whether at lower clock speed we can implement some kind of cache coherency between multiple pipeline. This is still on very much, I think, kind of a long distance goal for me. Anyone is interested on any of the topics, I am more than happy to do any kind of collaboration. Just let me know. I will try my best. So that's the short description of my system. And if you have any question, I'm here.
I have a way of maybe giving a specific example of the kind of restriction that I think Mihai was describing earlier. Do you mind if I give it a shot, Mihai, and see if I get it?
Yeah, sure. Of course.
So it's been a while since I've read the RMT paper, but if I remember correctly,
yes,
it might have described let's just say one variant of RMT is one where any container, any PHP container can, let's say if you want to calculate A plus B for value A in one PHP container and B in another PHP container, the simplest version of a hardware implementation you can imagine would be in a single stage. You can take an arbitrary container A and an arbitrary container B and add them together and get the result and put them in an arbitrary container.
Right.
But some implementations of RMT, to reduce cost of the size of the crossbar you would need to do that, put limitations and say, okay, this subset of containers, there's a full crossbar, and this subset of containers, full crossbar, but there isn't a full crossbar between the two sets of containers. And so there's certain values A plus B in certain container pairs that you just can't add together in that stage without copying into its own first. Do you try to, does your hardware description language try to model such hardware?
No, I have not implemented that.
Okay, thanks.
But I'm keeping, I think it will, I think in some of the discussion in the P4 group that I came to know that, and I have listed that I am keeping it in higher priority. Yep.
Did that answer your question, Mihai?
Yep.
Yeah. That's the kind of constraint, yes.
Yeah. But okay, let me give you an idea. Like I have like only one crossbar for the match and one crossbar for the action units. Okay, so that will be really easy to implement if I just put an option for multiple crossbar. I'll do that. Yeah, I'm keeping it at highest priority. Yeah, sure.
I had a question, which is, it was maybe it's cheating. I'm asking 2 in a row here, but do you early on, so for example, let's suppose your P4 program is just 2 tables, table A apply and table B apply.
Right.
And suppose that they are data independent. There's no data dependencies between them. Like table A has some actions that can modify some fields that are never used in table B.
Right.
So some P4 compilers will do a data dependency analysis of your tables and say, these are independent, they can be done in parallel.
Yeah, exactly. I do that.
Okay. Because my understanding is that the JSON, the P4C front and mid end don't do that, and the BMV2 JSON file doesn't.
Right. I do that. Particularly, I do that. I actually do the match and dependency, action dependency. There are 3 types of dependency mentioned in the standard P4 papers. I implement all those things.
Great. Thanks. Thanks. Any other questions for our speaker?
In fact, that also, my compiler backend also gives you the total packet processing delay in a pipeline based on those dependencies.
Billy, I see you have your hand raised. Or did?
Yeah, so I have first a question to clarify that my understanding is the JSON representation does not have the same amount of information as IR. Is that understanding correct?
I totally agree with that. That's why I mentioned that the P4C, the actual the C++ intermediate representation that gives a JSON. I can actually use that C++ based classes, but at that time, my focus was let's make something workable. So that's why I focused on the JSON representation for the specifically for the V1 model.
Yeah, thanks for the clarification.
It does contain that. I've looked at the BMV2JSON implementation in the past, Billy, and it's not a bad choice to start from, I think, for this kind of open source work.
I see.
The kind of things the kind of things it might leave out are like maybe some type information that you had in the source code.
Right,
It's converted all to bit vectors, for example, but not a lot.
Yeah, but for example, like for tables action, the actual like what happens in each action, are those encoded in the JSON or not?
Yes.
Yeah.
Okay, I see. Thanks.
Any other questions?
Oh, hello. Sorry, I can't find the raise my hand button, but I will
Speak up,
interject.
please.
Okay. Yeah, so I just kind of, I guess, had a meta comment on this. You kind of couched your presentation in the context of supporting the research community, but I think this is a very real problem in the implementation community. So we've implemented a fairly large network stack, all implemented in P4 and as interactions with the operating systems. And we have P4 and NICs, we have P4 and switches, we have P4 all over the place. And you know, the modern world was built on open compilers. If you imagine a world where we only had the compilers from the ASIC vendors like AMD and Intel, we wouldn't have the world that we have today. And when you're implementing things at a very low level, like in the operating system and things like that, you need an ISA to understand what's actually going on between the high-level languages and how they're implemented on the actual chips that they're running on. And so this is a very real problem for implementation too. And I would say, like a broader problem just for programmable networking in general that extends well beyond P4 is having the equivalent of an x86 or an ARM or a common ISA that we can target and actually have implementation and actually have this networking program or programmable networking idea actually become mainstream rather than kind of a niche thing that is used in academia and in a limited number of shops. And so I thank you very much for this presentation. I really appreciated it, and I hope to carry forward the conversation with folks about kind of going one step beyond what you've talked about today and actually defining an ISA that vendors can target, or even something like an intermediate language at the level of like LLVM SSA to be able to actually write compilers that target machine instruction level semantics to be able to really understand what's going on inside of our infrastructures that we're building on P4. So thank you, and I'll just kind of leave that meta comment there and hopefully spark further discussion.
Okay, I just want to add some of the comment on just beside your comment. Thanks for the appreciation. The reason I have mentioned research community is that, like, in my whole PhD life, I never got an access to real hardware. So I don't know, like, why whether it will be really applicable to the real hardware. So of course, you the people know that I have only knowledge on the research papers. So that's why I have mentioned the research community. And for the second thing you have mentioned, actually, like I have a lot of ideas and I have actually explored a couple of things. Like I have a goal, which I actually started working on, like from the mapping result, can we actually run them on any kind of x86 or ARM-based architecture? So it's like I started a bit of work on the Garnet simulator and the Gem5 environment. Then, like, due to lack of time, I just stopped that. But I will focus on that part also. And if the community just I get some kind of initiative starts, I will try to contribute that way.
Well, you know, a chip like Tofino looks more like an FPGA than a microprocessor.
Mm-hmm.
So there is no ISA really, a simple one at least.
Right. I agree. Yeah.
Yeah, I mean, I get the fact that like targeting a VLIW infrastructure is a lot different than targeting a superscalar infrastructure. It's a whole different animal. But I think the fundamental issue for systems implementers is that if we can't understand the translation of P4, which is a very high level language that leaves a ton of things up to the implementation, like just read what the semantics are for table size in the P4 spec, it means almost nothing. And so for like understanding translation from P4 spec to executable machine code with concrete semantics, like that has to be a thing. Otherwise, we can't do our job as systems builders.
Exactly. Yeah.
No, I can't remember how I came across Robin's work, but I came across it maybe a couple of weeks ago. Sorry, I probably had seen it before, but never paid close attention. And when I saw it a couple of weeks ago, I thought, I'm going to invite this guy for a talk, to give a talk. This looks interesting. And
Thanks a lot.
But I think, yeah.
Go ahead, Mihai.
So the fact that he never had access to hardware is bizarre because Intel has an academic program, and I think they.
I know that, but I didn't get access. Just let's maybe I can discuss it somewhere.
Sometimes I think Mihai requires a principal investigator, a full-time professor.
Right.
Backing
So
you.
your professor also needs some
themselves.
kind of budget, needs to spend some money, but
this stuff is expensive. Yeah.
Yeah. There's the reason. Exactly.
It depends on your professor as a grad student. Yeah.
And another alternative is for you to seek an internship to one of the places that build this stuff.
Yeah, I have tried, but I didn't get. That's the honest answer. I have applied like a lot of places for the actual programmable switch hardware, but I never got a call. Yeah, there's the reality. Yeah.
Everybody's got Robin's email today from the emails I've sent out the announcement. So feel free to send him an email if you're interested. Any other we have 3 minutes left until the top of the hour. Any other questions or comments for the speaker? All right. Yeah, and everybody has a link to the repo that Robin's published. And thanks for describing the limitations, Robin, because that's something that I had first and foremost in my mind as a grad student. If you had solved the Tofino compiler problem in open source, I would be flabbergasted. My jaw would be hitting the floor. But it looks like you bit off a lot of the interesting problems that at a high level, at the RMP paper level, that I would have expected you to tackle in this. And so thanks for a very clear, excellent talk, and looks interesting. And feel free to contact Robin if you're interested, or Robin, if you get feedback. Yeah, love to hear more. Any follow-ups if you come up with any other significant additions to this in the future.
Sure. If anyone have any kind of follow-up questions, just let me know. I'm more than open. You can either comment on the GitHub repo, or you can send me email. That's totally fine. And finally, I am really grateful and want to give me the opportunity to present my work here, and for all the excellent questions. Thank you all.
I'm going to stop the recording now, if I can remember where the button is.